Hello everybody, and welcome to the beginning of a brand new chapter. We are going to be looking at section 16.1. This starts out on page 54 for us. The topic of this section is the definite integral of a function of two variables. This chapter is going to be about integration in a multivariable setting. And I think the best way to start with this new topic is to look at an example, just kind of see how it works. Let's read this together. So the resort community of Deaniesville lies along the shore of Lake Fubini. Let rho of xy be the population density in people per square mile at the point xy, where x and y are measured in miles. Okay, and a table of values for this function is given below. Now, maybe one comment just on notation. So you heard me use the word rho when I read that. Okay, that letter looks like a P, but actually it's a Greek letter rho. You're welcome to call it P if you want to, but I'm going to call it rho. So this table that we're looking at over here actually gives us population densities at various positions. So we've got two position variables, y and x, and the y's are over here and the x's are up at the top, just to remember kind of how a table like this works. Okay, and then over here to the right is kind of a picture so that we can take those numbers and see where they're at on an actual grid of the town. Right, so why don't we start maybe by doing that. Notice, for example, that when y is equal to 0, we're actually down here in the picture. So if we wanted to take our population densities and write them in, the 10, 15, and 20 that you see would go here, here, and here in the picture. Okay, and then we'd come to y equals 5. Okay, that's actually sitting here. And so our population densities would be 9, 13, and 20 people per square mile. Okay, and then similarly 8, 11, and 14, just so we can kind of visually see where those population densities are. Okay, let's get rid of a little of the clutter here. Okay, and I'd like to make just kind of a general observation about the trend of these numbers that we're looking at. Notice that the smallest population densities appear to occur kind of up here in the upper left-hand corner, and the biggest ones in the lower right-hand corner. We're going to assume as we do this problem that that's a general trend, that that's sort of the way the population densities are distributed through this square that we're looking at. Okay, so that said, let's take a look at what we're being asked to do here. Okay, they would like us to approximate the population of Deaniesville for the rectangle 0 is less than or equal to xy is less than or equal to 10. Okay, that rectangle is actually a square. So we're just taking this region that we see in the picture and trying to give our best estimate of what the population would be based on the data. Okay, and the way that we do that is going to be kind of a logical method when you think about it. We have data about population density in people per square mile, so we're going to take densities, people per square mile, and multiply by areas to turn them into populations. And specifically, what we're going to do is to start by finding an overestimate of the population. And we're going to do it in kind of a square by square process. Think of taking our community and dividing it up into 4 squares. That's kind of a natural way to do it based on our data. So kind of starting with the square that I'm highlighting here. Okay, what if we wanted to overestimate the population just in that one square? Okay, well, what you could do is say, okay, if I want an overestimate, I'm going to look at the biggest population density, which in that case would be 13 at the lower right-hand corner, and assume that the population density is 13 over that entire subsquare. Okay, so we'll take 13, that's the population density, and multiply by the area. So what is the area of that subsquare? Okay, just the square that's in the upper left-hand corner here. Well, you can notice that that's a 5 by 5 square. So we'll get an area of 25, 5 times 5. Now let's do a quick units check here. So 13 was measured in people per square mile, and 5, those were distances, the length and the width of the square. So we're taking people per square mile times miles, and notice that if you cancel units, we get people. And that's good because we're trying to estimate population here. Okay, so that first term that we wrote down, there's our overestimate of the population in the first square, and we'll move on to the next one. Okay, so what about the square right to the right of that? Okay, well, same strategy. We want an overestimate, so we'll take the biggest population. That's going to be 20. And we will multiply it by its area, which is also 5 times 5. Okay, continuing on. Next square would be the lower left one. Biggest population density is 15. So we'll take 15 times 5 times 5. And then finally, 20. That's the biggest population in the lower right square. So we're going to get 20 times 5 times 5. Okay, next step would be to get a number for this. You might notice, just to save a little bit of writing, that every one of these terms has a 5 times 5 in it. That's a 25, and I'm going to go ahead and just factor that out. So we can write this a little shorter by writing 25 and then putting the populations after that, the 13, 20, 15, and 20. Okay, and if you do the arithmetic here, you can double check me on this, you're going to get 1700, and we already did the unit analysis and notice that we're going to get people as our units there. Okay, so there's an underestimate of the number of people that are in this town. Okay, next, we're going to do the same process and come up with an underestimate of the population. Okay, and to do this, same process, but now in each of these squares, we're going to look at the smallest populations and multiply them by their areas. Okay, so for the square in the upper left, what would be the lowest population density? It would be the 8 in the upper left-hand corner. And so we're going to take 8 times the area of the square. Okay, then we'd move on to the one just to the right of it. Smallest population density is in the upper left-hand corner, 11. So we'll take that 11, multiply by the area, and so on. Okay, and the last two minimum population densities would be the 9 and the 13. We're going to multiply those by their areas. Okay, do the same thing that we did before, factor out the 25. Okay, and if you do the arithmetic this time, you come up with 1,025 people. There's our underestimate. Okay, so what we could say so far in this problem is that we know that the population of this town, whatever it is, it's going to be between these two numbers that we have. Okay, and we could ask the question maybe, what would be a good overall estimate of the population? We've got a range of populations, but what would be a good overall estimate? Well, since one number is an overestimate and the other is an underestimate, we could maybe take the average. So our best estimate of the population, okay, would be just the average of these two numbers. Okay, and that turns out to be about 1363. Okay, now we have answered the question that they asked us here. We approximated the population, came up with 1363, but I want to pose a couple of other questions because it kind of leads us into the idea of an integral here. Okay, so number one, this is a pretty big range of values between 1025 and 1700. How could we make those two estimates more accurate? Okay, well, if you think about it, one way to do that would be to gather more population density data. If we had population density data for more points, these two numbers, the overestimate and the underestimate, would probably get closer together. Okay, so let's make that as a note here. Okay, we need more. And then we could ask the question, what would we need if we wanted to calculate the population exactly? Okay, well, that would be kind of like taking a limit. If we could know what the population density was at every single point in the square, okay, then we would essentially be taking a limit as the size of our little subsquares goes to 0, and we would ultimately wind up with the exact population. Okay, let's put that into words here. So if we had a formula for the density at every point in our square, we could calculate the exact population. All right, give ourselves a little bit of space here. So the exact population in that circumstance would kind of look like this. So we'd be taking a big sum of population densities, okay, at various points. I'm going to call those points xi and yj. We don't know for sure where they're at, but just think of them as density readings at points in our rectangle somewhere, and we'd be multiplying by the area of the rectangles, delta x, delta y. I don't want you to be intimidated by this notation. It's just kind of a general way of representing what we did above. We took densities times areas. That's exactly what's going on here, just written down in a more general form. And then to make that exact, we'd be taking the limit. Let me give myself just a bit more space here. We'd be taking a limit as the size of our rectangles goes to 0. That's what's going to make this exact. Okay, so you can imagine dividing that square into smaller and smaller and smaller pieces, getting more and more and more density data, and in the limit, we're going to get an exact population. Okay, well, there's a name for this limit that we're calculating. It's called a double integral. Okay, and our notation for it is going to look like this. Whoops, not f, rho. So the integral over r is just going to be the name for the rectangle that we're integrating over, rho of xy times dA. Okay, and this is called the double integral of rho over the rectangle r. Okay, we'll go ahead and make a comment what that r is that we're talking about. R is just a name for the region that we're integrating over. Okay, and there it is. And so the rest of this section will be talking about how do we think about this integral and how do we estimate it, kind of the way that we did in this example.